So for the entirety of this unit so far in electromagnetic radiation, we've looked at the wave aspect of light, but we haven't really done a rigorous analysis of what constitutes the wave model, nor have we really talked a lot about the evidence or like why people believe that light behaved as a wave. So we want to start to dip into that. So the big thing that we're going to be talking about is this thing called Young's double slit experiment. But before we can get into that, we have to talk about something else first. And the thing that we want to talk about is this thing called Hawkins Principle. Now, for those of you that are Dutch, I apologize for mispronouncing the name. I've tried, but it is what it is. But anyways, the wave model of light, it got some traction by Hooke. He kind of first proposed it, but the person who really took this the distance and really developed the framework for it was this gentleman from the Netherlands named Christian Huygens. Now, what he had said was actually quite revolutionary for the time. And at first it may not make a lot of sense, but bear with me, I'll try and sketch out a few things. So basically what Hawkins said is that if you have a wavefront itself consists of many little smaller wavelets. And these are what we would call the tiny secondary waves. Or actually, rather, let me reverse that. So what Hawkins said is that a wavefront, it's going to be consisting of several tiny secondary waves, and those tiny secondary waves are what we call wavelets. And then what's important is that those wavelets, they're going to propagate out in a concentric circle at the same speed as the wave itself, which is just a fancy way of saying same wavelength. And then we'd say that the line tangent to all those wavelets constitutes the wavefront. So this is known as Hawkins Principle. So basically what Hawkins Principle says is that a point on the wave, it's going to continue to propagate in a straight line away from its source, and basically it's going to be going out in all directions. So we can kind of see here this point source wave, it's going out in all directions. So if we kind of pick this wavefront here, or this is our wavefront, we can see that this wavefront is actually made up of smaller little wavelets, and then those wavelets are propagating out in tiny concentric circles. And then that curved tangent to the front of these wavelets, that makes up our wavefront. We could also look at this with a plane wave too. If I have my wavefront here, this wavefront's made up of these little wavelets here. Well, each of those wavelets is going to propagate out in concentric circles, and then the line tangent to those concentric circles, that is what we are going to have as our next wavefront. Now, where we might want to look at this, or where Hawkins Principle becomes a bit more important, is when we start to look at barriers. So I'm going to sketch this. We have this sketch here, but let me sketch something else here. So here's a barrier. So we're just going to have light. There's a barrier. And what I'm just going to sketch is I'm going to sketch the wavefronts that are approaching this barrier. So we have this wavefront. It's approaching this barrier. Now, if we were to treat light as a particle, what the particle model would say is, okay, well, with this barrier there, the light's going to be blocked here and here, and all we should see is light travel in a straight line through that barrier. But we've noticed that that's not quite the case. Now, what Hawkins Principle is going to say is that we're going to look at these little wavelets. Now, the first part is correct with this wave being blocked partially, like we have the barrier here and here. So this wavefront is going to be partially blocked. So I'm just going to kind of sketch the piece of the wave that actually goes through. But that little piece of the wave that goes through, this is going to be made up of secondary waves, or our little wavelets. Now, each of those wavelets that's passed through the barrier, they themselves are going to propagate out in concentric circles. And then we want to make sure that those concentric circles are roughly the same wavelength. So that's for my first wavelet there. I'm going to try to sketch in for my second wavelet. It's going to be a little more challenging. Yeah, a little bit of an ugly picture. So I apologize for that. I'm not really an artist. But this is really important. Even though we have that barrier there blocking a lot of the light, that light wave is still going to end up spreading out around the barrier because of Hawkins' principle, saying that these little wavelets, they spread out concentric circles. So these concentric circles are going to propagate outwards, and that light is going to fill in that space behind the barrier. It's almost going to look like there was no barrier there to begin with. And this whole idea of sound being able to kind of get around barriers of waves being able to bend around barriers or get around barriers, this is actually very applicable in real life. This is why, for example, if somebody is outside a door down a hallway, we can still hear them. What's happening is that sound wave is basically going around a barrier, going through a barrier, and then it's propagating out in concentric circles from that barrier. So even though we may be around a corner, we might not be able to see the person, we can still hear them because those waves can still make it around the corner because of Hawkins' Principle. So this idea of having light or any type of wave passing through a barrier and then it changing shape and direction, this change in shape and direction, or rather we can call this dispersion of energy, this is what is known as diffraction, and this is the last real big thing that we want to look at in this unit. So we are going to start to look at the diffraction of light. Hawkins' Principle kind of sets up the foundation for what we want to look at next with Young's double slit experiment. So Hawkins' Principle, this whole idea of treating the wavefront as a bunch of secondary waves that can propagate out in concentric circles, this allowed us to really set the foundation for the wave model of light, and then of course to explain Young's experimental results in his experiment that we're going to look at next.